Towards the end of the lecture yesterday, we introduced this idea of torque. It's the rotational analog of force, as we will see. And we have some fixed, in this, we're dealing with fixed axes of rotation here. And the torque about the axis is defined like this. The general derivation, the general definition is R cross F. So we've got an axis here. There's a point of application of the force here. There's an R vector here. You take R, you want to move it up here, do R cross F. So it's the magnitude of the 2 times the sine of the angle between the two vectors. And you know that's got to be there, because what's important for the rotational dynamics here is just this the tangential component. So that sine of the angle there, that gives you the tangential component. So before we do dynamics, there's one more thing we want to do. We want to look at the gravitational torque. This will be useful for a problem we're going to solve later today. Let's suppose we have a uniform rod that's pivoted. Here's the axis down here. It's in a uniform gravitational field. And you know, if I release it from rest here, it's going to angularly accelerate, right? So what's the torque? It's the torque that's doing the angular acceleration, as we will see, which is not surprising. What is the torque? At this point, it's a good example to find the torque on here. Now looks like there's a problem here. I can imagine splitting this up into a bunch of little tiny masses, right? Each of those little masses contributes to the torque. So do we have to integrate to do this? The answer is no. We can actually we can deal with any system, an arbitrary system, anything in a uniform gravitational field. We can look at the torque about a point. So this is one of these perhaps deceptively simple arguments here. So I've got a system of particles, an arbitrary system of particles. Okay, this is just one possible example. And I've got these masses here, individual masses, and they're at some vector location from the axis. Okay, the total torque is going to be the sum of all the individual torques. So each little mass is going to contribute this torque. It's the force here, the weight, which is the force, and I have to cross it with R. So this is going to be the total torque in general. Now this mass is just a scalar, so I can move it. Instead of having it multiplied by G here, I can move it over and have it multiply R. I can commute that, or I can move this mass over here. I don't change this product here. And the reason we do that is, once we've got the mi over here, this factor right here, this g factor, is a constant. It doesn't depend upon I. It's just a constant vector. So I can factor it out of the sum, and I get this. Now if you have trouble seeing this step going from here to here, guess how people see it. What do you think people do if they want to believe the step that I did from here to here? What would you do?
Hit the I believe button.
That makes you believe it? I've never heard of the I believe button before. Just hitting a button helps you believe something? Boy, the digital age, I don't know, there's some disadvantages to the digital age. No, you take two masses, consider a system of two masses, write out the sum. Explicitly write it out, and you'll see that you can factor this. You can see that this step is correct. That's what people do. That's what physicists do. That's what I do. Just write it out, to help you believe it. Now, what's this? This looks familiar, doesn't it? It's the moment. And remember, we have this relationship that it's actually our definition. We talked about what kind of what do they have now? It's 1 over the total mass times the sum of all the moments. Remember that? It's actually a definition. We motivated it. So I recognize here that this has to be the total mass times the distance to the center of mass. Now we move the total mass back to here, And now we have one more center of mass theorem. The gravitational torque on any system of particles, continuous or discrete, doesn't matter. You can imagine all the mass to be concentrated at the center of mass and find the torque of that. That's what this says here. This is R to the center of mass, and we're imagining, this is the force, total force on the system, the total mass times G. So we'll use this later, okay? Now we can apply this we'll use it later actually for this system. And now we imagine all the mass concentrate at the center of mass. There'll be a weight mg. That's going to cause a torque. The torque is R cross mg, okay? And this is R. So the angle between the two vectors is actually not the angle we're given. You got to add 90 degrees. But in the end, you get that it's going to be the cosine of theta. And actually, an easier way of looking at this is we're imagining all the mass to be concentrated at the center of mass, and we're finding the torque on that. There's this force going down here. The easier way to find the torque is to take this force and multiply by the moment arm, isn't it? They're equivalent. We talked about that yesterday. The moment arm here is this distance, and you can see it's mg times the cosine of, it's L over 2 times the cosine of theta. This distance right here is the hypotenuse times the cosine of theta. That directly gets you at the answer. Okay, so we'll look at this, we'll use this expression later on today. Okay, so now finally we're ready to do dynamics. And to begin, we have this fixed axis, we have an arbit. This denotes, a peanut, I don't think I've told you guys this, but something that looks like a peanut means an arbitrary body. I don't know, everybody does that. Nobody knows why. I don't know if anybody cares, but this peanut type looking thing denotes it's an arbitrary system, arbitrary rigid body. It can be anything. Okay, it could be this, could be a dumbbell with mass, it's anything. It's arbitrary, a general system. Let's imagine that we exert a force at a point here. The point is a distance r from the axis. Over a brief interval of time, that force can do work. And the work is defined to be the force dotted with the displacement. We defined that's that long ago. Well, it's not that long ago, but it seems long ago, right? That's the work done. Now, what is, when I dot, here's my displacement. When I dot the force with dr, we can think of that as just picking out the tangential component of the force, right? When I dot these two vectors, it's going to be dr, times the magnitude times the cosine of theta, but I can think of that, as we've seen before, as just this component. So let's put that in here. When I do the dot product, I get the tangential component of the force times dr. And dr here, this little differential displacement here, right, is given by r d theta. I see a thin little triangle here. And you remember our definition of the radian measure that I told you was convenient? Here's yet one more example. The angular displacement here in radians is dr divided by r in the limit of a thin triangle. You really have to take the arc length, but this is differential. This is so tiny that the radian measure of this angular displacement here, going from here to here, just a little bit, is going to be that divided by that. So what we conclude here, what's this? That's the torque we're just talking about. So for rotational dynamics here, a little bit of work done by a force or a torque is the torque times a little bit of angle. And it's exactly analogous to the translational case. Remember this? dw is equal to f dx for one-dimensional translational motion. Remember that? So you don't need to remember this. You should, at this point, I think you probably, it's hard not to remember this. To get the rotational case, we just use the analog of the force, which is the torque, and the analog of the displacement, dx, which is d theta. Okay, so now, finally, we can derive Newton's law for the rotational motion here. And we're going to use the kinetic energy, work kinetic energy theorem. And if you think about that, or if you go back and look at it, that was entirely general. It works for any system. We found that the work done by the net force is the change in kinetic energy. And I know we were thinking of translational motion there, but it's totally general. It doesn't matter. If you go back and look at the derivation, even though we had translational thoughts in our head, that's what we were thinking about applying this to. If you look back at the derivation, it doesn't care. It could be, it's any kind of motion, okay? It includes rotational motion. So here it is, it's over any interval of time. We're going to look at over a differential interval of time like we did here, okay? So that means the differential amount of work done by the net force is the change in kinetic energy. So for a rotational system with a fixed axis, the work done is going to be, by the net force, is going to be the net torque times d theta. We just showed that, okay? Except we didn't have a net here, we just did it for any force, but it's going to be true for the net torque too. That's what's important here. So the work done by the net force is the net torque times the angular displacement. The differential change in kinetic energy, the kinetic energy is 1/2 I omega squared, right? Which is really easy to remember because it's analogous to 1/2 mv squared. So we take a differential of this for constant, we're a rigid body, the moment of inertia about the axis is not changing. So we take a differential of this, it's just constant. We get this, and now we set these two things equal, all right? And now we divide by dt, and on the left-hand side, yeah, so I get d theta dt, I get d omega dt here, so dividing by dt gives me this, but this is just omega. D theta dt is by definition omega. So I can cancel these omegas, and I end up with the net torque is the moment of inertia times d omega dt, and that we call alpha, the angular acceleration. So we get this. And why is this easy to remember? It looks like F equals ma, doesn't it? Except we have to use the rotational analogs. Instead of force, the net force, we use the net torque. Instead of the mass, we have the moment of inertia. Instead of the acceleration, we have the angular acceleration. So there's this direct analogy here that just we keep building on. It's easy to remember. So this is called Newton's second law for rotational motion, and I should add there about a fixed axis. We're doing this all for a fixed axis. We will generalize this in the next chapter. So you'll notice here that if we fix the moment of inertia, okay, the angular acceleration responding to a torque is proportional to the torque. If I double the net torque for a fixed moment of inertia, I'm going to double the angular acceleration. For if you have a fixed torque, right? If this is fixed, this is a constant, then the angular acceleration is inversely proportional to the moment of inertia. And this is just analogous to when I try to accelerate something. I got a certain force I'm going to exert on it. If I increase the mass, it's going to have less acceleration, and they're in inverse proportion. So the same thing has happened rotationally here. Okay, so I need 2 volunteers. So this is commercial apparatus. We went through a lot of trouble, had some summer high school students, like 3 or 4 years ago, we went through, and Gene will remember this, we went through a lot of trouble to make our own, because it's a great demo, as you'll see. And then like a year later, this company came out with these things. We didn't invent this. This has been around since the 80s. I saw it in the 80s. Okay, so I still need 2 volunteers. Okay, we have 1. You won't be harmed in the in the doing of this film. Okay, so they both, so you guys can stand, just make sure you give yourself, okay, just a second. So they both have the same weight. They both have the same weight, okay? Which means if I exert a force here, they're both going to have the same acceleration. Same force, same acceleration, right? Okay, so here's what I want you guys to do. I want you to hold, each of you hold one of these, and I want you to, not yet, I want you to rotate as fast as you can back and forth, about a roughly 45 degree, as fast as you can, okay? On 3.
Want to switch?
Sure.
Okay,
Not towards each other though, right?
1, 2, 3. Okay. So
That's why.
and you after class you can, oh thank you. After class you can really feel. Damon really felt the rotational inertia. I mean, it is real. I mean, this one is just easy. So you can. Oh no, this was a lot slower, right? The acceleration was. I thought you guys noticed that.
No, I didn't.
Well, you were doing it. Maybe it's because you were doing it. Yeah. Did everyone? I mean, I can do the demo right. I'm doing the demo right now, right? I'm trying to push this.
I didn't know any better.
Okay, you're out of this, right? Just be quiet. What did you guys notice? Did you notice the big difference?
Yeah.
Okay, thank you. Okay.
Because that had more to do with arm muscle.
So you can probably guess what was going on there, right? So even though these have the same mass, there's metal weights in there. We use lead. They didn't. I looked it up an hour ago. Pascal didn't tell us what they use. But here's the idea. Both of these have the same mass, right? You can see they got the same type of weights, same length here. But when I rotate it like this, there's a big difference here. And you can try this one too. So even though they have the same mass, their moments of inertia are different. And they differ by a lot here, because remember, it depends upon the square of the distance. So when you compare these two, I got this mass at this little distance here. I've got this one way out here. I take the ratio of those two distances, and then I got to square it for the moment of inertia. Yeah. Incidentally, we did this. This was part of thesis research. Recently, with the ones we made and the ones Pascal made, we measured the ratio of the moments of inertia, and it's about 7.7. And they advertised it at 6. I don't know how they came up with that number. So I'm going to be calling them, tell them they're underselling their apparatus. And this is even greater. The ratio of the moments of inertia here is even greater. Okay, any questions about that? Okay. So I think I finally figured this out. This has been plaguing me for years. We have 3 different apparatus like this. The idea here is that this hanging weight here is going to attach to a cord here about some radius, is going to angularly accelerate this disk. Right? And we want to exhibit the fact that when if you increase, for a fixed moment of inertia, if you increase the torque, you get a bigger angular acceleration, right? And we want to also exhibit the fact that for a fixed torque, if you increase the moment of inertia, you get less angular acceleration, okay? We have 3 different apparatuses, and none of them works, none of them is they're all inadequate. They're all inadequate. So this is the most recent one we bought a couple of years ago. And I finally figured out how we're gonna modify this. I finally figured out, and I'll tell you how we're gonna modify it in a moment. But let's look here. You can see that I've got the string wrapped around this the smallest diameter here. There's 3 possible diameters. Okay, and now if I apply now there's a torque on this. There's going to be a torque, right? We got this weight here, we got this moment arm here. And so when I let this go, there's going to be an angular acceleration. If I add mass to this, what's going to happen to the angular acceleration? It's so obvious, we're going to save time and just not do that demo, okay? We're going to do, there's 3 possible demos here. We're going to skip that one because it's so obvious. Now the problem here is that I'm going to drive it at this rate, and then I'm going to put it on the maximum here. And the acceleration is, we expect it to be bigger because the torque is bigger now. We've increased the moment arm, right? It should have greater angular acceleration, but it's not easy to see. So I'm going to time it. I like 3 revolutions. So I'm going to hit this on 1, 2, 3. So, uh-oh, is that it right there?
Yeah.
1, 2, 3. I think I did that right. What is this? Okay, it's around 11, okay. Now let's go back. You got to keep your head out of the way here. Now, I just made a change. What is it?
You went to the larger diameter.
Yeah, and it's not even a factor of 2, okay? These people who design this stuff, I don't know what goes on or what does not go on in their minds. So, let me reset this. So now, we've got a bigger torque here. 1, 2, 3. 1, 2. I think you can see that it was greater, but it wasn't real dramatic. But this shows it, okay? So that's an example. We have obviously we haven't altered the body. It's the moment of inertia is fixed. We increase the torque, we get a greater angular acceleration. And the 2 are going to be proportional. That's Newton's second law for rotation about a fixed axis. Now what I'm going to do, the second demonstration here, so I'm going to bring this back up. We're going to stick with our same, we're going to stick with the same weight here. Okay, but now look at this. Now, am I changing the mass of the body? No, but I'm changing it, aren't I? What am I changing? A moment of inertia. And in fact, because it depends upon the square of the distance, now we don't need the stop clock now. That's the way it ought to be between the different radii. It ought to be very obvious like that. Obviously less. We've increased the moment of inertia, and we're getting clearly less angular acceleration. So here's the fix. It took me a while to figure this out. I had other ideas, but this hub thing here, this is actually machined out of one piece of aluminum. I talked to our model maker yesterday. He can go in and see this small diameter here. He can put this on a lathe, take all this stuff off, and get in there and turn that radius down. This diameter, turn it down on a lathe by a factor of 2. That should do it. Then it should be obvious. You won't need to do this. Okay, any questions about that? Let's see, let me put it here. Questions?
So when you move the masses out to the extreme edges of each of the arms, having it really slow down but increase the moment of inertia, but we're still using it, and that in fact increased the torque, right? If I understand that right.
No, it didn't. We didn't do anything to the. All right, technically you're right. I didn't want to get into this. What's the torque here? We've got this weight. It's at a distance. What's the torque? Well, you'd think it would be the weight time. Well, not when you let it go, because once it starts accelerating, the tension's not going to be mg in that cord, is it? It's going to be less. We'll solve problems like that. But unfortunately, you seem to have stumbled across that. So let's see how can we get around this. So we increased the moment of inertia, right? But that was the only change that I made. We applied the force at the same diameter, same radius, and we had the same hanging weight.
So essentially it's the same net torque. It's just the acceleration had to have decreased.
Yeah, but it's actually not the same torque, because when it has less angular acceleration, the mass is accelerating less, so the tension's going to be greater. Yeah, let's. Are you following me? It's a little tricky. It's a little bit. Pardon me?
Let's skip it.
Yeah, I think it would be better to skip it. This is better to bring up when we're doing problems. Okay? Yeah. I thought for sure. Oh, no one's going to ask. No one's going to. We're not. I can avoid that. I'm going to word it carefully so that I'm being correct. But you guys won't know what I'm worried about. It's almost like students have this extra sense where they can tell when instructor's trying to put something over on them. I've noticed this. It's they pick up on it. I don't know if it's the sweat or I don't know what it is, but they pick up on something. Okay, so let's look at an example now. Okay, and this is where we can actually. I think you'll be able to see what we were just talking about. This is a simple problem. We have a uniform disk. We're applying the force at the rim. Okay, like imagine wrapping string iron like we did there. We have some mass here. This is big M. We'll call this little m. And we want to, let's find the acceleration of m here, okay? Let's go after that, the acceleration of m. There's also going to be an angular acceleration. But as you see, it's very simply related to the acceleration of this. So there's the diagram. Now we draw force diagrams. Here's our picture. Let's draw a force diagram for this mass. Well, there's a tension force up. There's the weight down, right? And we're going to choose down as positive here. So here's the net force on the mass. It must be the mass times the acceleration. We've done this a zillion times. No question about that, okay? Now, of course, the problem here is that we have one equation and two unknowns. We don't know the acceleration, that's what we're trying to find, and we don't know the tension. So we got to look to the pulley here. We got to look at the pulley. Now, the pulley has a force diagram. It has a weight due to gravity, and then there's a force here. The support is exerting an equal and opposite upward force. So the center of mass has no acceleration. No velocity for that matter either. So that's not important. What's important is the rotations, the rotational motion of the cylinder. So we need to draw what we could call a torque diagram as opposed to a force diagram. Here's the disk. There's a force exerted here. That force is the same. It's equal and opposite to the force on here. It's the tension force. Okay, by Newton's third law, it's going to be the tension force. So, what does Newton's second law for rotations tell us here? The torque is the tension times r, must be the moment of inertia times the angular acceleration. That's F equals ma for rotational motion, as we just discussed. I know the moment of inertia. What's the moment of inertia of a disk? A uniform disk has moment of inertia, remember, 1/2 mr squared? You'll get used to that. We'll do a lot of problems with disks. So there's the moment of inertia, and here's alpha. So I can simplify this. I can cancel an r. I can get an expression for t here. It's equal to this. Now, what's alpha? Well, we don't know alpha. But we know the chord. We're going to assume that the chord is not slipping, right? So that has a very important consequence here. If the chord is not slipping, the velocity of the chord at any point is going to be the same as the velocity of a point on the disk, right? Because it's not slipping. So that means that the acceleration here is going to be the same as the acceleration of a point on the disk. I know what the acceleration of a point on the disk is because I know that v is equal to omega r. Remember that? A velocity of the point on the disk is omega times r. I differentiate this with respect to time, and I know that alpha has to be alpha r. So this is the final ingredient we need to solve this problem, because we actually have another unknown here. We have two equations, and we have three unknowns. We don't know A, we don't know T, we don't know alpha. But A and alpha are constrained. Because the cord doesn't slip, we got to have A is equal to alpha R. So once we substitute that in there, we have this for the tension, we can plug it into there, and we can solve for the acceleration. And we get a simple answer. Here it is. The acceleration is, imagine the G over here, it's mg, that's the driving force here. And then the effective inertia of this system involves not just the mass, we see the little m in there, downstairs, right, because F is equal to ma, but we see an additional effect, inertia effect, due to the rotation of the pulley, due to the rotation of the disk there. But it's not the mass, you know, why is that factor of 2 there? You might guess that it would just, oh, the center of mass is at the center of the disk. But you're getting there. Why don't we just, you might guess that this would be the answer. It's because the moment of inertia, it's the inertia here is going to depend upon how that mass is distributed. If I have a pulley here where all the mass is concentrated at the center and it's very light out here, there'll be no inertia. It'll be essentially 0 down here. The 2 comes from right here. I equals 1/2 mr squared. That's where it comes from. So the information of the moment of inertia is in here, and it's in that factor of the mass there. Okay, I have a note here, but it's not important. So that's our first problem in rotational dynamics, isn't it? First example. Anybody have any questions? So you can see it's similar to the translational stuff. It's just we got to do a torque diagram now. So we'll do a number of problems like this. Here's a good one. One of the first problems we did in translational motion was we had this system with 2 masses, gravity, and then we had an ideal pulley here, massless, frictionless pulley. Remember that? And we solved that problem. We found the acceleration. Well, now let's find it if we have a massive pulley. We're still going to assume no friction, but now let's say we have a pulley, and we're not going to specify. You know, actual pulleys, I don't want to look at that thing. They're not uniform disks, right? They usually have a more complicated geometry, but they're going to have a moment of inertia about the axis. So we're going to be more realistic here. We're just going to call this I and leave it unspecified. We know what it is. It's something. We just leave it unspecified. So if you want to apply our result to an actual pulley, you're going to have to find what the moment of inertia of that pulley is. And you know, 1/2 mr squared is just going to be typically a rough approximation, because the mass distribution can have spokes, right? There's all kinds of pulleys out there, but each of them will have a moment of inertia. You may have to put it on a computer to find out what it is, right? Or do an experiment similar to this. You can look at it from a different perspective. So how do we solve this problem? Well, now we're going to have 3 force diagrams, or we're having a force diagram for this, a force diagram for this, and a torque diagram for the pulley. So here's the force diagram for the mass on the horizontal surface, frictionless surface, normal force, blah, 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 you know this. There's going to be a tension force here that moves that along. Over here, this is similar to what we just did. We're going to have a force diagram like this with a tension force impeding the motion. Right? And you'll notice here that I've called this T1, the tension in here T1 and the tension there T2. Why did I do that? Isn't there just one tension here? In the past, it's always been one tension.
But because of the pulley, you have to account for different tensions now, right?
Yeah, you're getting there. Why do we have to have different tensions? In fact, why does T2 have to be bigger than T1? This may not be obvious. We start off with the system at rest, right? We let it go. It's clear that there's going to be some angular acceleration there. There's got to be a torque that causes that. How do I get a torque on that pulley? I got to have this tension force being greater than that tension force. It's got to be. That's troublesome. Is that bothering you? I can see that. But it has to be. So there's, there has to be static frictional force here. If there were no friction, what would happen? The pulley wouldn't rotate. Okay, so we have this static frictional force, and we've got to have a bigger force. To get this to accelerate, we've got to have a net force here. And it's due to the fact that the tension has to be greater here than it is there. So we can write down our Newton's second law here. This is the typical case we've done before. We just did this. We've done it many times before. And now for the rotational diagram, I have a tension force here, tension force here. The net torque, calling this the positive direction, because we're going to call this, we've called this positive down again, right? There's a positive force. So the net torque, sum of these two torques, this is a negative torque, both acting at the same radius. That must be the moment of inertia times the angular acceleration. And because there's no slippage here, the angular acceleration is A over R. A is equal to alpha R for the same reason as in the last example. And now you can see mathematically here, if the tensions were the same, you'd be in a lot of trouble. You would conclude that there's no acceleration. Which would be the case if I held this mass here, then the tensions would be the same. But that's, that's trivial. That's a static problem. We want to look at the dynamic problem here. So we have three equations. How many unknowns do we have? With T1, T2, and A. Three equations, three unknowns. And they're linear. So we can solve these. The easiest way to solve them, actually, if you think about it, is to just add them up. Add all the left-hand sides and add all the right-hand sides. Why would somebody want to do that? Look at the left, look at this. Oh, first of all, divide by R. Sorry. Divide by R, make that an R squared. Now, what happens when I add this equation to this equation? The T1's going to cancel. When I add this equation to that equation, the T2 is going to cancel. There are unknowns that we don't really care about here. We want to find the acceleration. So when you do that, you collapse it down to one equation and one unknown, and here's the acceleration that you get. There's the acceleration. So you may remember that, and it's such a simple result, when we did the ideal pulley, the pulley that had no mass, this is the answer that we got. That's a special case of this, when I is equal to 0. Now the effect of the inertia of the pulley is, it has to be a mass here, and you can't just put the moment of inertia in there. That doesn't have the right dimensions, but it turns out to be I divided by R squared. This has dimensions of mass, and that's the effective mass here. Yeah?
So we know that T2 is greater than T1, but what about the friction as, from on M1 on, I guess you can call it the table?
That's assumed to be 0 here.
Okay.
Yeah, I don't know if I said that, but yeah, this is a. So this relates to that first problem. Remember the first problem we solved? We hadn't even talked about friction at that point. So we were assuming not just an ideal pulley, and I don't know if ideal pulleys are. We were assuming a massless, frictionless pulley. We were also assuming a frictionless surface. Okay, so we'll be doing problems like this tomorrow, right? Tomorrow. Okay, now let's look at let's go back to this. Remember, let's go back to that problem. And what we're going to ask here, and you'll see why, it's maybe not evident right now, but the interesting thing to look at here is the tangential acceleration of the free end. If you look at the free end here, over any little interval of time here, it's going to have, it's got a centripetal acceleration. We know that, v squared over r. But it's also, because this is angularly accelerating, it will have some tangential angular acceleration. It'll have actually, it'll have some angular acceleration. It will also have, the point on the end will have some tangential acceleration, the point on the end, in meters per second squared, okay? Linear. Okay, so how do we get that? Well, here's the picture, right? And here's Newton's second law for rotations about a fixed axis. What's the moment of inertia of a rod about its end? I don't know if you remember that. It's the 1/3. Not the 1/12. That's why it's good, just forget about the one. It's 1/3 about the end. Remember that we talked about that?
Yesterday.
I guess it was just yesterday. It seems like it was 2 days ago. Okay. All right, so that's the moment of inertia. That's good. What's the torque? Well, we calculated that earlier. Remember, that's what we started off with today. This is the torque. You can look back at that if you don't remember it. So Newton's second law for rotations here tells us that the angular acceleration has to be the torque divided by the moment of inertia. I plug in the torque, the expression for the torque. I plug in the 1/3 ml squared, and I can simplify, and now we find this is alpha. And we can't really do anything with this. That's what it is. So this is the angular acceleration, so many radians per second squared. Is it constant here? No, it depends upon theta. So right in the beginning, when right in the beginning, incidentally, I don't know if I said this here. It doesn't really matter, but if we imagine actually doing an experiment here, one way we can do it is we could release this from rest at the top, right? Now technically, if it's perfectly balanced and I release it from rest, what's going to happen? It'll stay there, right? And if there are no fluctuations, no air in the room, and this was a perfect support, and you don't worry about quantum mechanics. This is a classical mechanics course, right? So forget I said quantum mechanics, but that will actually cause it to eventually move. But anyway, classically, that thing will just stay there. So I want to imagine releasing it with the just slightest angle. If I put in this very small angle this way, I release it, what's it going to do? Well, it's going to spend a lot of time up there, but eventually it's going to be clear that it's angularly accelerating, right? So we can check that. When theta is equal to 90, what's the cosine of 90 degrees?
0.
And so we get no angular acceleration. And it's going to be the greatest when we have the greatest torque down here. Incidentally, the reason this is not constant is we don't have constant torque here. The torque is 0 here. It's going to be a maximum here because the moment arm is the biggest distance here. The moment arm starts at 0 here. The force is going right through the axis. So the moment arm here is increasing, and it's going to be the maximum here. So let's look at the acceleration like it's mentioned here. Let's look at the acceleration of the end. We know that all along the rod here, v is equal to omega r, right? And if I differentiate, we talked about this before, if I differentiate this with respect to time, I get that the tangential acceleration is alpha times r, because the d omega dt is alpha. And then if we look at the point on the end, we need to multiply by L. This r here becomes L for the end. So this is the tangential acceleration at the end, and we get this expression. So again, at theta is equal to 90 degrees, it's 0. That's a check. That's a check on our solution. And the big surprise here is, what is the acceleration when theta is equal to 0? Does that bother anybody? It's greater than g. How can this be greater than g? Is there a mistake? There's no mistake. No mistake. So we can demonstrate this. Here's a classic demonstration. And this needs to be improved too. Yeah, but I'm not going to get into it. So this is a golf tee. There's a ball on top. Most people use a golf ball because this is a golf tee. But this works, the wooden ball works better, I think. Now, I'm going to abruptly remove this prop right here. This mass is going to fall straight down. It's going to have acceleration g. And drag is negligible. Over these distances, drag is negligible. right? This cup, this is the problem we just solved. The Planck here is going to angularly accelerate. And we've predicted at the end here that it has an angular acceleration greater than g. So what's going to happen here is this is designed such that when this goes down here, the cup is right below the initial location of the ball. Okay? So here's the idea. The ball falls straight down. This, which is about at the same level, travels a bigger distance. So you might think, since it's normal to think that this thing can't have acceleration greater than g, that there's no way the ball could land in the cup. That's what you would think, okay? But our theory tells us that the end it has an acceleration greater at near 90 degrees, and it's going to happen, come in greater and greater, that it has acceleration greater than g. So what do you think is going to happen here? Okay, I did it about half a dozen times, and it landed in the cup every time. Let's try it again. It's supposed to land in the cup. It might have landed there and bounced out. Did anybody notice? Hit the rim? Okay, let me try it again here. Okay, it went in there. So because that was a greater distance here, this thing has to be there. It has to be time. It has to have an average acceleration bigger than g, or it wouldn't have been able to land in the cup. So that's kind of a dramatic demonstration, and I don't think the manufacturers realized that there's actually another demonstration you can do here. What's nice about demos? Let's go over here. So it looks like the theory's true, right? But we can test it in another way. We can test that in another way. We can test it directly. What's going to happen when I release this? Well, the theory says it has an acceleration greater than g. This is going to go at g, so what's going to happen?
It's going to hit the floor before the ball does.
Well, what you want to look at is right in the beginning here, the fact that this accelerates fast enough that they will separate. So 1, 2, 3. Did you see the separation there? Right. So one student pointed out, I think it was last year, that this is like where is it here? It's like a dunk tank. And people sit on something like, okay. If that helps you, great. But I guess it is useful because it gets this plank, this thing the person's sitting on, out of the way for the person, so the person, yeah, so it may serve some use there. Okay. Now, what's happening here is this. When you, let's say right here, when you release this from rest, when I go like this end has acceleration, it's 3/2 g, right? The reason it's greater than g is there are internal stresses in this rod here to keep it rigid, to keep the rod rigid. If I had a noodle here, if I drop this up here like this and this thing stays rigid, if I have something that's really flexible, it's going to kind of go like this, right? It's going to, if you imagine having a flat surface and putting a noodle, a wet noodle, a cooked noodle, right? Okay. If I remove this abruptly, it's going to do something like this. Well, a rigid object like this is going to remain straight, and the only way it can remain straight is there's a force exerted along from a mass element here to mass element here. There's a force exerted to keep this thing straight. So at the end here, it's going to be biggest at the end here. That keeps to keep this rod straight. This thing has to accelerate greater than g. There's a down, in addition to, on the little bit of mass at the end here, in addition to gravity, there's this stress, there's a force due to the rod acting down on this thing. That's why it's there. Okay, so the final thing to do here is there are two problems here. I don't know if, let me just illustrate them here. We're going to use energy conservation to solve some problems. So let's go back to our, here's this one, the one we were just looking at, this problem. Let's ask if it's released from rest at the top, what is the instantaneous angular velocity at the bottom here? So we got an initial state, we got a final state, we don't care about the time. It's a mechanical energy is going to be conserved here, there are no losses. So this screams out for energy conservation, right? The initial energy has to equal the final energy because we're not dissipating any mechanical energy here. So mechanical energy will be conserved. I'm going to naturally call zero potential energy here. We'll call that zero. We can do it anywhere here. So initially there is some potential energy. What is the initial potential energy? Remember the center of mass formula, theorem here? We can imagine all the mass to be concentrated at the center of mass. And that gives us the potential energy. That's one of the center of mass theorems, or whatever you want to call it. Finally, what's the potential energy at this point right here, in this moment right here? Zero potential energy. It's all kinetic. So we write down, this is really easy. Here's the initial potential energy. The initial energy, which is all potential. The final energy is all kinetic, 1/2 I omega squared. I know I here for a rod. I equate these two, and I can solve for omega. And incidentally, the velocity at the end here would be omega times L, and it's this. And when something falls from rest over height, this thing's moving faster. So that's the same effect that we saw before about the greater acceleration here. It's popping up here. It's not a 2, it's a 3. Okay, the final problem here, this is also, we're going to use energy conservation here. And this gets back to this, this demo that we did before. We have a hanging mass driving this disk. It's a frictionless, uniform disk of mass 5, yes, a uniform disk of mass 5 kilograms. And we release it from rest. You will, are we going to do this in a lab? I can't remember. I think we might do it. Yeah. There's a rotational dynamics lab. You guys have done, how many labs have you
Three.
There's one more, and it's going to involve rotational motion, and you will actually do this. I'm pretty sure, I think. Something similar to this, very similar to this. So let's say we release this mass from rest, and we let it fall a certain specified distance, 2 centimeters. For you, it'll hit the floor, okay? So, right before it hits the floor, what's the velocity of the mass? Well, again, this is energy conservation, right? We have an initial energy. If we call this our zero potential energy, we have an initial energy, mgh. This m times g times that height right there, that must be the final energy. Now, what's the final energy, final mechanical energy here? Where is it? Where does it reside? Well, this mass is moving, right? 1/2 mv squared. But what about this? Yeah, we have rotational kinetic energy. And they're connected by the fact that v has to equal omega r because the cord is not slipping. So you use that fact and you can find the final angular velocity. And oh, by the way, we already solved this problem earlier. Because the acceleration is constant here, we can use our previous, if you look back just today, remember this, we found this? So we looked at this similar problem before here. Because the acceleration is constant, we can use that fact and the no time equation, and we get the same answer. All right. Sorry I went over.